Welcome to Study Loop.
This is chapter 21, problem number 72. We have a resonant circuit whose capacitance is given as 260 nanofarads. Let's do the conversion, 260 times 10 to the power of negative 9 farads. And the resonant frequency is, well, F naught is 18 kilohertz. Let's convert that to hertz when we're at it. As you know, there's a conversion goes at 10 to the power of 3 hertz. So this inductor is closely packed, and the coils, well, it's a closely packed coil, a set of coils stacked on top of each other, right? That's what a coil is. So the total length of the wire that is used to generate this inductor is 12 meters. This is not the height of the coil. This is the length of the wire that is wrapped around the coil, right? And the diameter of this wire is given to us as 1.1 millimeters. Let's convert that to meters while we're at it. Okay. Now, the question is, how many loops will the inductor contain? So we are looking for the number of turns, right? So what we basically have, let me draw it here. Assume that this is our inductor. Let's say for every winding, right, this distance, which corresponds to the diameter of the wire, is given to us. The cross-sectional area here, the diameter, let's call it capital D, because this is something else. Let's not get it confused with the diameter of the wire. We're looking, you're going to see that in the equations, we were looking for the length of the solenoid, which is different than this L here. L is the amount of wire, again, the length of the wire that is used. So if for one winding, imagine this is the top view, the amount of wire that would be used to form this is 2 pi capital R, let's call it. This capital R being the radius of the solenoid. It has nothing to do with the wire's radius, right? So then if you have one turn this long, then overall, what we would have for, let's say, one winding is 2 pi r long, right? Then for n winding, we would have L wire divided by this 2 pi r. Is that right? So then also from n, we can go to the L of the solenoid. The length of the solenoid, I'm going to call L sol, is going to be equal to the number of turns times the diameter of the wire, right? Because if you have 2 turns, let's say you're sweeping 2 times d wire here. So imagine that we're doing this all the way up until we reach the length of the solenoid. So these are important equations that we're going to use. So keep that in mind on the side. Now, going back to the main equation, first of all, we're given the resonant frequency, and let's remember what resonant frequency equation looks like. So it's F naught equals 1 over 2 pi square root of the inductance times the capacitance, right? And we have the inductance here, L. Let's remember what L was. L is mu naught n squared over times A over L for a solenoid, right? Again, this is why we needed to do this, because we need the length of the entire solenoid. This area here, as you know, is this cross-sectional area of the solenoid. So this is going to be equal to pi. Well, let's call the radius of the solenoid capital R. It's going to be pi r squared, just to remind you. And L sol, the length of the solenoid, is going to be n times d wire. But for now, I suggest that we first take the square of both sides in this equation. And let me go to the new page here. So F naught squared is going to be equal to 1 over 4 pi squared L times C, right? So this, let's get L out of this equation. So L, then the inductance is going to be equal to 1 over 4 pi squared F naught squared times C. So then from the inductance equation for a solenoid, that equals to mu naught n squared over cross-section area divided by the length of the solenoid, right? So now all we need to do is to remember what cross-section area was here. Again, this area here is pi r squared, and n was, let's remember, it was L wire over 2 pi r. And L solenoid, we wrote an expression for that too. L solenoid was N times D wire, right? All we need to do is just to plug everything, all these three equations, in the inductance equation. So then what we have is L equals 1 over 4 pi squared F naught squared C equals mu naught N is L wire over 2 pi r squared, because we have n squared here, times pi r squared over L solenoid is n times d wire. Then, as you can see, well, the pi r squared cancels this pi r squared, and well, then what we have on the right-hand side is mu naught L wire squared. Well, the 1 pi cancels out, right? We still have another pi here. So L wire over n times pi times the wire. Now, going back to the left-hand side of this equation, this equals to 1 over 4 pi squared F naught squared times C. We have, and we also have 4 here, right? Because we have square of 2 in denominator. So from here, 4s are going to cancel out. 1 pi is going to cancel out. And we can isolate n out of this equation. So it's going to be n equals mu naught L wire pi F naught squared times C over D wire. So this is going to be our main equation. Again, this stands for mu naught L wire times pi times F naught squared times the capacitance over D wire. Now all we need to do is to plug in the numerical values. Again, mu naught is 4 pi times 10 to the power -7 Tesla meter over amp. And we have the length of the wire squared, right? Length of the wire squared. So it's 12 meters squared. Then we have pi. And then we have F naught. Remember what F naught was? It's 18 times 10 to the power 3 hertz. 18 times 10 to the power 3 hertz. But we're going to square that, right? Squared times the capacitance was 260 times 10 to the power -9. 260 times 10 to the power -9 amperes. Then over the diameter of the wire was 1.1 times 10 to the power -3 meters. So when we plug in the numerical values, we're going to see that this corresponds to 43.49. Well, since you have to have an integer number as the number of turns, you could actually say that this equals to 43 turns, right?